We've reached a point where modern silicon architectures have effectively solved the processing problem for the majority of users. System-on-a-chip designs, particularly Apple's M series, deliver a volume of computational headroom that most daily software simply cannot exhaust. Because those limits are rarely tested, buying a new machine solely for a faster CPU or GPU offers steep diminishing returns for standard workflows. For the modern professional, the core processor is no longer the primary constraint dictating operational efficiency. The actual friction point has moved to the physical ports. When moving massive datasets onto an external drive, the connection protocol dictates the pace. We define this as I/O throughput, the specific rate at which data travels back and forth between the internal processor and external storage devices. The integration of the new Thunderbolt 5 protocol essentially dismantles that historical data bottleneck. This standard pushes external disk transfer speeds well past the theoretical 5,000 megabyte per second threshold. Think of the architecture as a direct physical pipeline, routing straight out from the M5 chip to your external drive array. Historically, that single connection line restricted the volume of data flow, forcing external speeds to lag behind internal storage. Mastering this physical pipeline is the definitive way to drastically reduce transfer times in professional workflows. To test the empirical limits of this new bandwidth, we start with the current M5 hardware architecture. We pair that with a specific external storage requirement, a 4 TB Rocket Extreme SSD from Sabrent. But raw storage isn't enough. The SSD media must be housed inside a chassis engineered specifically to handle this new throughput protocol. The final piece of physical hardware required is a dedicated Thunderbolt 5 cable. Attempting to route this data through older generation cables instantly throttles the transfer rate, negating the entire hardware setup. Achieving maximum throughput requires an unbroken, fully compliant hardware chain, extending from the processor directly into the storage media. To measure this pipeline in action, we begin with the industry-standard Blackmagic Disk Speed Test application. This interface provides our initial data readout, giving us 2 primary speed dials to track the drive's baseline read and write performance. When we initiate the test, the read speed hits exactly 5,000 megabytes per second. The write metric climbs slightly higher, registering 5,100 megabytes per second. Look closely at the absolute upper boundary of those dials. The needles are pinned entirely against the edge. The actual hardware transfer speeds are colliding with the hard-coded limits of the testing software itself. The application is technically topping out before the hardware pipeline actually reaches its true maximum capacity. When external hardware components outpace the legacy diagnostic tools used to measure them, professionals have to rethink how they calculate their system ceilings. We switch our testing methodology to amorphous disk mark, an application built with much higher empirical measurement ceilings. Plotting the initial Blackmagic peak against the new amorphous benchmark reveals a clear discrepancy. By removing the software constraint, we expose the true unthrottled throughput capacity flowing through that Thunderbolt 5 pipeline. To isolate the port's specific contribution, we run a control test, routing the exact same Sabrent drive and cable through a previous generation Thunderbolt 4 port. Moving to the older protocol immediately cuts the empirical hardware performance in half. The solid-state drive is perfectly capable of maintaining the higher state, but it is bottlenecked entirely by the older port standard. This is a massive, single-generation doubling of bandwidth capacity, dictated solely by the I/O connection. Consider the actual experience of upgrading from an M3 or M4 chip to the new M5 for standard computing tasks. Because standard workflows rarely demand high data transfer volumes, the raw processor bump remains largely invisible to the end user. But when you map computational requirements against data transfer demands during heavy professional workflows, the bottleneck becomes obvious. The measurable, physical benefit of this current generation of hardware lies almost entirely in those invisible I/O protocol advancements. This reality shifts the criteria for deciding when a professional should actually invest in a new workstation. Capital investments in hardware should be calculated by your external data transfer requirements rather than arbitrary computational benchmark scores. We are looking at the physical reality of moving massive raw digital assets instantly across a totally unconstrained hardware pipeline. Moving a terabyte of raw video on a legacy system means waiting. On the Thunderbolt 5 standard, that exact same transfer happens in minutes. For data-heavy workflows, mastering that throughput is the definitive metric that must dictate future upgrade cycles.